Jain, welcome to the course Network Analysis and Synthesis, and we are discussing the graph theory of this course. So if you remember, in the last class we discussed what is the importance of graph theory, and we also discussed some terminology related to the graph theory, and in this we just stopped here. What is planar, non-planar and isomorphic graphs? So in the last lecture we stopped here. Today we are going to discuss remaining topics of this course, that is what is tree, then what is cotree, links, basic loop, or you can say the tie set, basic cut set, and incident matrices. So today we are going to discuss different matrices that are being used in graph theory to solve or to carry out the network analysis, and the remaining are the matrices and duality, and in the last we carry out the loop and node analysis. So today we will just focus on this topic: what is the tree and what are the different matrices that are being used in graph theory. So what is tree? So tree is defined as a connected subgraph of a connected graph. So tree is a subgraph of original graph which contains all the nodes of the original graph but does not contain any loop. So it means we have a graph is given, so graph G is given, and we have to take a subgraph. Take a subgraph in such a way that it contains all the nodes of the original graph G but does not contain any loop. So in a tree, there is a tree of a graph, there is one and only one path between every pair of nodes. We will see later on by doing some examples. And the another term is twigs. So what is twig? Twig is the branch of a tree, and these branches are removed from the graph in forming a tree. So a graph is, suppose a graph is given. Suppose I am taking one graph. This is your graph. Okay. So these are the branches of the graph. Six and 7. So this is the graph, original graph G. Original graph G. We take a subgraph of this graph in such a way that it contains all the nodes. So these are the these are the nodes 1, 2, 3 and 4, and these are the branches. Branches are in brackets, nodes are in circles, just to differentiate between the branches and nodes. So this is a subgraph. It contains all the nodes this is your 2 and this is your 3. So it contains all the nodes but does not contain any loop. There is no any closed path, and we may able to go from 1 to 2, 1 to 3, 2 to 4, 2 to 3, 2 to 1, 1 to 4, and so we can go. So all the nodes are connected and it does not form any loop. So it is a tree. So what are the twigs? Tree branches are called twigs. So in this case 1, 2, 3, they are the twigs. And what are the links? Branches removed from the graph in forming a tree are called links. So what are the links for this case? Links are 4, 5, 6, 7. So twigs are 1, 2, 3 and links are 4, 5, 6, 7. So it is defined as a connected subgraph. Connected means all the nodes are connected. Means there exists at least one path from every node to other nodes of the graph. Then the set of all links corresponding to a given tree is called a cotree. So for this particular graph, we can draw a tree. We can draw a cotree. So what is cotree? Remaining. So this is your four links. So links are basically dotted line. This. So this is your 7. This is your 6. This is your 4, and this is your 5. So these are this is cotree. To set up all links corresponding to a given tree. So for this particular tree, we have taken this as a tree. So for this tree, this is cotree. Complement of a tree is called cotree. So there exists a cotree for every tree of the graph. Okay. So in a graph there may be n number of trees. That we'll discuss later on. How many trees are possible in this particular graph, we will discuss later on. So we take one tree, then there will be a cotree. A cotree may or may not be a connected graph and may or may not contain slope. So in the case of tree, the nodes must be connected or the graph should be connected and it does not contain any loop. But in the case of cotree, it may or may not be connected or it may or may not contain any loop. Suppose if graph has n nodes, its tree will have n minus 1 branches, twigs. So in this case n is equal to 4. The number of twigs is equal to n minus 1. Twigs is equal to n minus 1. So n minus 1, 4 minus 1 is equal to 3. 3. N minus 1. And the number of twigs is equal to t is equal to n minus 1 is the known as tree value of the graph. And the number of n minus 2 is also known as rank of the tree. How can we find the rank of the tree? That is equal to n minus 1. And the number of links, that is L. This is L. This is basically L. Corresponding to any tree of the graph is B minus T. B the number of branches. B is number of branches. Number of branches of original graph. Of original graph G. So how many branches are there? There are 7 branches. And T is how many twigs? Twigs is 3. So 7 minus 3, 4. So number of links will be 4. So B minus N plus 1. So these are the relationship between how many twigs, how many links, okay, we can get. So this is about the tree. So tree is applicable to a disconnected graph. Connected graph. If the graph is disconnected, then we have the concept is forest. We have to take each tree from the each connected subgraph. Now the next topic is the incidence matrix. What is the incidence matrix? So for a given oriented graph, it is easy to tell to which branches are incident at which nodes and what are their orientations. Suppose I am taking this graph, oriented graph. Again oriented graph. 7, this is your 1, this is your 2, 3, 4. So for a given oriented graph, it is easy to tell at which branches are incident at which nodes. Suppose this is the branch 1, this is your, this is 2. This is 2. So, which branches are incident at which nodes and what are their orientations relative to the node? So, suppose branch A is in between node 1 and node 2. Okay, and its orientation is away from the node 1. So, the branch 1 incident at node 1 and 2 and its orientation is away from the node 1. So this incidence information of the branches of a graph, of the oriented graph, the graph must be oriented. Oriented graph can be given in a concise mathematical form by a matrix. So it is called incidence matrix. So for a given oriented graph having n nodes and b branches, the complete incidence matrix denoted by AA is a rectangular matrix of order n into b. So if the oriented graph is containing n nodes and b branches, the incident matrix will have n rows and b columns. So order is n into b, so n number of rows and b number of columns. And the interest, so we suppose we have this is the matrix, this is your matrix, 1 2 3 4 5 6 7 columns, 1 2 3 4 nodes. Okay, so matrix has some elements. Say this is your A11, this is your A11, A12, A17, A21, A27, A41 and A47. So interest Aij. Aij means ith node, jth branch, or you can say the ith row, jth column. Is the ith row corresponding to the ith node and jth branch corresponding to jth column is corresponding to the jth branch. So suppose A11. So what is the value of A11? It can be given as, look at here, this is the ith node and jth branch. If the incident at ith node and orientation is away from the ith node, so this Aij will be 1. Look at here. So this element A11 will be 1. Okay. Suppose this jth branch is incident at node I and its orientation is towards node I. So Aij will be -1. And the third condition is, if the jth branch is not incident on node I, so the value of Aij will be 0. So this way we can transfer this graph, this information into a concise mathematical form, which is known as incidence matrix. Because we are representing in the matrix form, so it is called incident matrix. And incident means which branches are incident at which node and what are their orientations. So there is another term related to this incidence matrix, and this matrix is called reduced matrix, and this matrix is generally used in network analysis. So what is reduced incident matrix? Suppose if we eliminate one row of the matrix AA, the resulting matrix is called reduced incidence matrix, and simply we can say an incidence matrix, and it is denoted by A. and its order will be n minus 1 into b, one number of rows. So it is our usual practice to eliminate that row from the complete incidence matrix which corresponds to the reference of the network. So a network is given, we take the reference node and network is transformed into the graph. So there will a reference node corresponding to the reference node of the network, and corresponding to that row in the matrix we eliminate. And the rank of both matrix A and A is n minus 1. Suppose we have matrix A 1 2 3 4 1 2 3 4 5 6 7. Okay, this is A11, A17, A41, A47. Okay, so we eliminate. Suppose this node 4 is the reference node. So this A is of 1, 2, 3, and number of columns will be the number of branches. So this is the reduced incidence matrix. So there are some properties. What are the properties? The unit entries 1 or minus 1 in a row identify the branches incident at a node, and their number is the degree of the node. Columns of A with entries in two identical rows correspond to the two branches with same end nodes, and hence they are in the parallel. Third property is a degree of 1 for a row means that there is only one branch incident at the node, and this is possible in a tree, we can see, and we have seen that if the degree of a node is 2, it shows exactly two branches are incident at the node, and hence these branches are in series. And this is the most important: how many trees are there in a oriented graph we can find. So number of possible trees is the determinant of matrix A into A transpose. So A matrix is given, this A matrix is given, then we take A transpose, then multiply A transpose, and we take the determinant, that is the number of trees. So how many possible trees are there in a oriented graph, that will be given by this relationship. We draw the complete incidence matrix, eliminate one row, usually reference node, and the resulting matrix is A. Take the transpose, multiply A matrix with A transpose, and take the determinant of that matrix, will give the number of possible trees in a graph. So this is suppose this is the oriented graph, and this is your complete incident matrix. How many nodes are there? 1, 2, 3, 4 nodes. So 4 rows. How many branches? 7 branches. So 7 columns. And we can see that branch 1 is incident at node 1 and 2, and its orientation away from the node 1. So for this A11, this is positive, and for this A21, it is minus 1, and remaining elements are 0. Similarly, branch 2, it is in between node 2 and node 3, and its orientation is away from the node 3. So 3, 2. So 3, 2 will be 1. Here 3, 2. 3 2 will be 1 and 2 2 this will be the minus 1. Branch 3 away from the 2, so it is plus, towards 4 it is minus. Branch 4 away from the 1, so it is plus 1, towards 3, so it is minus 1. 5 away from 3, so it is minus 1, and towards 4 it is minus 1. 6 is towards 1, so it is minus 1, and away from the 4, so it is 1. And 7, we can see that it is away from the 1, so it is plus 1, and towards 4 it is minus 1. And we can see that the summation is 0. Summation of column is 0, 0, 0, 0, 0, 0. So in the examples, if the matrix is given, so we can easily identify whether the given matrix is complete incident matrix or reduced incident matrix. So how can you find out? Just take the summation of column. If it is coming 0, then the given matrix is the complete incident matrix. If it is not 0, then the given matrix is reduced incident matrix. Now the another term is loop. So what is loop? So loop, or we can say the maze or a circuit, is possible in a connected subgraph in which each node has degree of 2, that is exactly 2 branches are incident on each node of the loop. So this is a graph, okay, and I have taken one tree. So how many loops are there? We can see that 1, 2, 3, 4. 4 loops. Then we have outer, then inner. So there are n number of loops are there, okay. But we are interested in any loop, the number of nodes must be equal to the number of branches. But we are interested in fundamental loop. We know that any closed path is called loop, but we are interested in fundamental loop. So remember, fundamental loop is defined for a tree. So a oriented graph is given. So you have to select a tree. So I have selected 1, 2, 3 as a tree branches, and we can see that how many fundamental loops are there. So what is the definition? Whenever a link is added to a tree, a fundamental loop will be formed, and this is called fundamental loop. So thus, suppose I am adding one link here, because 4, 5, 6, 7 they are the links. They have removed from the graph in formation of this tree. So 4, 5, 6. So this is one loop. This is one loop, and say this is the corresponding to the link 4. So it is called, I am just giving the name L4. Okay. A fundamental loop of a graph with respect to tree is the format of one link and unique set of twigs. So we can see that this is a fundamental loop having 3 branches, 1, 2, 4. So 4 is link and 1, 2 are twigs. And at the same time, the fundamental loop, one more thing is, how will orient a loop? So the orientation of fundamental loop is as per its defining links. So links की direction ऐसे है, तो we can draw all the fundamental loops here. So suppose I am adding this link 5. So this is your another fundamental loop. Then I am adding branch number 6. So this is also called fundamental loop, and this is say called L6. So this is L6, and we have another link which is 7. So 7. So this is the fundamental loop. This is 1. This is called L7. So we can see that how many fundamental loops are there? There are 4 fundamental loops. So number of fundamental loops are equal to the number of links. So there will be the 4 fundamental loops. Although there will be a number of loops, but fundamental loop will be only 4. So how can you identify? How can formation? Add a link, and a loop will be formed. And we have to orient. Orientation is as per its defining links. Suppose here we can draw all the fundamental loops. So suppose this is your tree. So we can, this is your L4. So this is your L4, and this is the twigs. Then the another fundamental loop is this one. One, 3, 6. So this is your L6. Okay. Another fundamental loop is, this is your 2. This is your 2. So 2, 3. This is your 2, 3, and 5. This is your 5. So this is your L5. And one more, because there is one more. Links is there. So this is 7. This is your 1, and this is your 3. And orientation is like this. L7. So L5, L4. So orientation of this fundamental loop is as per its defining links. Link. So this is your 3. This is your 3. 2, 3, 5. 1, 3, 7. 1, 3, 6. And 1, 2, 4. So these are the fundamental loops of any given graph. So fundamental loops is applicable to a tree. So to identify or to draw the fundamental loops, we have to select a tree. Already discussed by the same as defining links. And the branch voltage is positive if the orientation coincides with that of the fundamental loop. So we can write all the KVLs. So fundamental loops, suppose I can write there the previous here. Here we can write the KVL. So here L4. So L4, so minus V1 voltage of this branch minus V2 plus V4 is 0. So let apply KVL. Apply KVL means let the V1, V2, V3, V4, V5, V6, V7 are the branch voltages. So in this loop, so 2 and 4, the orientation of 4 and 2, they are coinciding. So they will be plus, and it is opposite to 1, so minus 1. L5, we can see here. So 5 positive, 3 minus, or 2 minus. So minus V2 minus V3 plus V5 is equal to 0. L6 this. So 1, 3, 6 all positive. V1 plus V3 plus V6 is equal to 0. And L7 this. So we can see that opposite to 1, 3. So minus 1 minus 3 plus V7. Sorry. So minus V3 plus V7. So these are the KVL equations. So these KVL equations can be written in the matrix form. So in the next slides we have written all the Kirchhoff's voltage law for the fundamental loops. So for the loop 1 means corresponding to link 4, link 5, link 6 and link 7. So there are 4 fundamental loops. So these equations can be written in a matrix form. So this is the matrix. V1, V2, V3, V4, they are the branch voltages. They are the branch voltages. Okay. So this matrix is called Tysett matrix or fundamental loop matrix. So this is Bij, ith loop and jth branch, if the coinciding one not if the opposing -1 does not involve 0. So these are the entries of this matrix. This is the Tysett matrix. Okay. So now there is another term, mesh matrix. So mesh matrix, if the graph is planar, so there is an alternate way of selecting b minus 1 plus n. So these are the independent loops. So this is achieved by selecting meshes instead of fundamental loops. So by definition, a mesh is a loop in which there are no branches in its interior. It is general practice to orient all the meshes either in the clockwise or anti-clockwise direction. So I am stopping here. In the next lecture, I will start from this mesh matrix. So we start with the mesh matrix, and there is another matrix, that is the fundamental cut-set matrix. So in the next class, we will discuss the fundamental cut-set matrix and the mesh matrix. So how the mesh matrix is different from the Tysett matrix, and then after that we will carry out some examples using these matrices to solve a network. So thank you very much. Jai Hind.